Hello, welcome again. Today's flip lecture is quite similar to my previous flip lecture. In my previous flip lecture, I was describing to you the transient response for second order, time response for second order transfer functions. So we considered what happens when we have different kinds of second order transfer functions, which can be no damping, underdamped, critically damped, or overdamped system. How does the response change? And also at the end of the lecture, I described to you what are the different time response specifications for an underdamped case. Today, we'll continue discussion assuming a second order transfer function, the same transfer function that we had for the previous flip lecture. But the main purpose of this lecture is to understand the trends. So we wish to understand how, if we have poles which for this transfer function which move around in the S plane, like they have different real values or imaginary values, what does it do to the different time response specifications? For example, does it increase the settling time or does it decrease the settling time if we move the poles in a certain direction? Does it increase the peak time or reduce the peak time if we move in certain directions? Does it increase the overshoot or decrease the overshoot if we move in a certain direction? So we will continue the discussion with this transfer function. And as I mentioned in the last lecture, we found that the poles of this kind of a transfer function can be found by solving the characteristic equation, which is taking denominator equal to 0. And we find that the poles are given by these expressions, where both the real part and the imaginary part are functions of damping factor and the natural frequency. Notice that the real part of the real part of the pole is zeta times omega n, and the imaginary part is omega n times square root of 1 minus zeta square, which is referred as the damped natural frequency. So damped natural frequency is basically, for the underdamped system, the time period of the oscillation. If I'm trying to find out the time period of the oscillation for the underdamped system, I can look at the time that it takes between two troughs or two peaks, and this time period is going to be equal to 2 pi divided by omega d. This is in contrast to assuming that there is no damping factor. So if we assume that the damping factor is equal to 0, then the time period of the oscillations, so these oscillations are not going to decay. So the time period of these oscillations is going to be related to the natural frequency. So it is 2 pi divided by omega n. Both omega n and omega d have the units of radians per second. In the last lecture, we looked at the step response for an underdamped system, and we described that the step response for the underdamped system is given by this expression. All these time response specifications that I described, the settling time, peak time, rise time, overshoot, peak response, they were all found assuming this expression of the response. In this response, we have a constant term, which is determining the steady state value, a sinusoidal term, which is determining the oscillation characteristics, and an exponential term, which is determining how the oscillations decay over time. The sinusoidal term is having an argument of omega d times omega d multiplied with time plus theta, which is the initial phase. Omega d is basically the damped oscillation frequency, so determines the period of the oscillation. The exponential is to the power minus zeta omega n t, where zeta omega n is just the real part of the pole that we described above. So the real part of the pole is also determining how fast the oscillations are going to get attenuated. This the location of poles on the S plane can be described by this figure. I think that this figure is quite important. So this shows that for certain values of omega n and zeta, the distance of the pole from the origin is given by omega n. The real part is given by zeta omega n. The imaginary part is given by omega d. The angle with respect to the negative real axis is given by theta, where theta is nothing but cos inverse of zeta. So this can be found easily by trigonometry. So we can look at the we can basically just look at the cos theta is base divided by the hypotenuse, and the base is zeta omega n. Hypotenuse is omega n, so we can get this relationship. I think even though you can derive this expressions based on some of these expressions are also there in the list of formulas, but I think you can memorize this figure because it will be these relationships will be used quite often. This is also describing the figure next to it is also describing what happens if we keep omega n to be constant and zeta increases from 0 to infinity. When zeta is equal to 0, we are at the imaginary axis. When zeta is between 0 and infinity, between 0 and 1, when zeta is between 0 and 1, we have the underdamped case where the poles follow a semicircular arc. So as we are changing a parameter and we are looking at the plot that the poles take, this is a family of pole locations, and this family of pole locations is also referred as the locus of the pole locations. So in this case, we are looking at the locus of the second order poles as zeta is changing from 0 to infinity. So this segment where it follows the semicircular arc, but the distance of this semicircular arc will always be given by the natural frequency omega n, is the case when we have underdamped case, okay? When we have an underdamped system. When zeta ends up being equal to 1, then we have two real poles, and they both are located at the distance of omega n along the negative real axis. So we have two real poles at negative omega n, negative omega n. If I continue increasing zeta, so if I continue increasing zeta above 1 and approach infinity, one of the pole is going to approach the origin. One of the pole is going to approach origin, while the other pole is going to approach infinity. But they are never going to quite reach there. So they will continue coming closer to the imaginary axis, while the other pole continues to move further away from the imaginary axis. Let us see what happens if we try to fix up certain parameters in these pole locations, like fixing up the real part of the pole, or fixing up the imaginary part of the pole, or fixing up the angle that the pole takes with the negative real axis. So in the previous lecture, I described to you these formulas where the settling time was given by 4 times zeta omega n. You can see that if I fix up the real part of the pole, all the poles are going to decay according to the same exponential attenuation function, which is described by this dotted curve, which means that they are going to reach within the 2% of the settling time in the same amount of time. So if I fix up the real part of the pole, the settling time of the settling time of different the settling time is going to get fixed. However, as I go further away from the real axis, so if the imaginary part continues increasing, notice that the peak response happens at pi divided by omega d. So the peak time will continue becoming smaller. So if I continue going in the direction with higher imaginary components, my response, I will reach the peak response faster. So my curves are going to shift in the direction as shown by the arrow over here. Let us look at the next curve where I have fixed the imaginary part of the pole. Now the imaginary part of the pole is fixed. The damped oscillation period has fixed. The peak time is, as I described, is going from one trough to the next peak. So I start my response, I'm at the trough of the response. Then I go to the peak value of the response, which is the next peak. So this is half of the damped oscillation period. So by fixing up the imaginary part of the pole, I fixed up the damped oscillation period. I fixed up the peak time of the response. All the curves, all the transfer functions having, all the second order transfer functions having poles with the same imaginary component will have the same peak time. However, if I move my real part of the pole, if my real part of the pole increases, then my system is going to get settle faster because the settling time is going to reduce. So if I go further away from the imaginary axis, my settling time will be faster. So it will be more similar to here the fastest settling time is for the curve which is closest to the equilibrium condition, so the pink curve, whereas the slowest, the curve that takes longest to settle down is the blue curve. So as I move further away from the imaginary axis, I'll end up settling faster. So I'll end up having curves which are described by this arrow. Finally, let us consider the case in which all the transfer functions, second order transfer functions that I consider, have the same lie on the same diagonal which passes through the origin, lie on the same inclined angle that passes through the origin. So the angle that I have with the negative real axis is the same. Since the angle with the negative real axis is the same, therefore the damping factor is fixed. The overshoot or the peak response were based on just the peak response or overshoot were basically based on just the damping factor. So there was no natural frequency in the formula. So all these curves which are having the same angle with respect to the negative real axis will reach the same maximum value with respect to the equilibrium. So in this case, they will have the same percentage overshoot with respect to the equilibrium. However, if I go further away, if I go further from the origin, both the real part as well as the imaginary part are increasing. Therefore, both the settling time as well as the peak time are decreasing. So you can see in this case that if I go further away from the imaginary axis, the curves are going to shift in the direction as shown by the arrow over here. So that finishes this flipped lecture. Thank you.